We're going to do 11.3a, and we're going to deal with the correlation regression file that's in Rossman OneChance. So you're going to need a Chromebook, and I'll do the first one, and then you guys can do the other. So I'm just going to click on this, and this is the correlation regression, and we are choosing, this one is, it is foot length and height. So on the other ones, you're just going to have to choose a different data set, whatever data set it tells you. Okay, so I'm going to use this data. Okay, and the first question says, which variable do you think makes more sense to use as the explanatory variable, and which is the response variable? So if we are measuring foot length and height, now I believe, I'm just sort of guessing here, I think that foot length is in centimeters and height is in inches. I have no idea why you would measure it that way. You would need two different rulers, but my guess is that's what they did. They measured foot length in centimeters and height in inches, but I don't have any way to prove that. That's just sort of my guess. So which one explains the other? Neither. They sort of just are both your body size, right? As you grow, your foot gets longer and you get taller. So in this case, it doesn't really matter which one you choose as the explanatory and which one you choose as the response. And numerically, it doesn't matter at all. But when you are doing a statistical study, it makes sense to put the explanatory on the x-axis. Now, just because you do that does not mean that the x explains the y. There might be a confounding variable, and in this case, the confounding variable is just growth. Okay. Next question. So, what form does this come in? And that's basically saying, is it linear, quadratic, or something else? This one looks pretty linear. Oh, that one dot is not really there. Let me get rid of that. That was me making mistakes. Okay, so this is a linear situation. And how would you categorize the direction? Is it going up or down? Positive. Okay. And then the strength. It's moderately strong. It's not super predictive. And then do anything unusual about it? Well, this is kind of an outlier. If I were to remove the 2456 person, then, so this would kind of be my football, but if I got rid of that guy or gal, then that would be more predictive, right? Should we throw that person away? Yes. What would be a good reason for throwing that person away? If we know something is wrong about them. So maybe they were born, well, I guess they have feet, so maybe they don't have a femur, right? So their feet are 24 centimeters long, but their height is 56, but they don't have a femur bone, right? They're missing their knee. Their hip is attached to their lower leg. I don't know. But that would be a good reason to toss that person out, right? It's not fair to compare femur people with femurless people. I don't know, something like that. So you only get rid of something in the data if you know that there is a mistake in there. You don't just throw it out because it's not convenient. Okay? So it's just asking, are there any unusual things about it? And we would just say, yes, this person is an outlier. The femurless child. I was going to say they don't have a torso, but that doesn't really make sense, right? Okay. You wouldn't measure wingspan of a person who's missing one arm, right? I mean, you could, but you're not going to compare them to everybody else to make predictions. Okay. So, the value of the correlation coefficient, we've talked about that before. So the correlation coefficient is this right here, 0.711. And the correlation coefficient, how big and small can it be? It can go up to 1 and down to -1. What does the correlation coefficient tell us? It's the shape of the football. Is it a football? Is it a frisbee? Is it a circle? And it's sort of a value that that tells us how good a prediction would be if we use the regression line. Okay? So today we're introducing a new term, and it is R squared. So R squared is exactly what it sounds like. You take the R value and you square it. Okay? Now the R squared value has a very specific definition, and it's sort of hard to understand. Okay? So if I were to draw the average height of all people, how good of a prediction is that average height? So basically, a person walks in and their foot length is 28. What is my prediction for their height? 66, right? What if somebody comes in with 24 centimeter foot length? What's my prediction for height? 66. What about 32? 66. So if every single person that walks in is given a predicted value of 66, how accurate is that prediction going to be? Not very accurate. Okay? But if I draw the regression line, which would be the center of every column, remember, oh, actually I don't need to do that. Well, let's see how close I am. Oh, so close. Okay? How accurate is that prediction line? Well, this prediction is 50% more accurate than the average. So the R squared value is a percentage that determines how much of the X value, or sorry, how much of the Y value can be predicted using the X value. And it's a comparison to just guessing the average, right? So how good of a prediction is an R value of 0.711? It's a little deceptive because a 0.7 is actually twice as accurate as a 0.5 on the R value. But when you square the R value, you get this number that gives you how much better of a prediction it's going to be. So we are 50% more accurate if we use the regression line than if we just guess the average. And the way we like to say this is, and I don't want to say it wrong, so look at the answers. Letter E, 50.6% of the variation in height is associated with a linear increase in foot length. Okay? So about half of your height is predictable by how long your foot is. Okay? Now, predictions are going to be messy, right? No prediction for foot and height is going to be perfectly accurate because people are just different sizes. And there is not a one-to-one relationship between foot length and height. But knowing that 50% of your height can be predicted using your foot length tells us about how accurate a height prediction is going to be using your foot length. Now, what if that number was 95%? Then we can very accurately predict your height using your foot length. What if that R squared value was 5%? Well, then your foot length would tell us almost nothing about your height. Does that make sense? So what are the what are the bounds on r squared? How big can it be? How small can it be? Well, r ranges from -1 to 1. So r squared is going to range from 0 to 1. R squared is always positive. R squared does not care about direction, right? It just cares about the shape of the football. And if you have an r value of 0.5, is your r squared going to be bigger or smaller than that? Smaller. 0.5 times 0.5 is 25%. Okay? So what if your r value was 0.7? Your r squared is going to be about 0.49. So you can see here that an r value of 1/2 can predict about 25% of your height, whereas an r value of 0.7 predicts about 50% of your height. So a 0.7 football is twice as accurate as a 0.5 football. That's what the r squared value tells you. Okay? All right, next up. Okay, F. Determine the equation of the least squares line. So that is this line right here. 38.3 plus 1.03 times your foot length. Okay. So the next question asks, interpret the value of the slope of the coefficient in context. So what does this number tell us? Don't look at the answer. It's the rise over run. So what does it mean in this story? For every, so let's say rise over run, and so I'm going to put 1.03 inches over 1 centimeter. So what does that tell us? For every 1 inch increase in, 1 centimeter increase in foot length, that corresponds to a 1.0 centimeter increase in height. So basically the slope of the regression line is always for a 1 unit increase in x, we have a corresponding increase in y, which could be greater than 1 or less than 1. It just depends on the situation. Okay, letter H, what does this represent? It is a starting point, but what does it mean in the context of this scenario? Somebody with a foot length of 0, x is 0, they would be 38.3 inches tall. Now, does anybody have a foot length of 0? Not really. There are people without feet, right? That's not what we're talking about. We mean if you take a person and you shrink them down vertically until their foot length is 0, how tall are they? So what that's saying is if we follow this backwards, so it's going to be way over here, and we look at people with 20 centimeter foot lengths, 19, 18, 17, all the way down to 0, a person with a 0 length foot would be 38.3 inches tall. Okay? Does that make any sense in this situation? No. So the y-intercept in this case is not really a possibility. I believe that's a question, right? Yeah. Is this a context for which the value of the intercept provides relevant information? No, it doesn't. Okay. Now let's say you had a graph where you were making hats. Okay, then you had a 0, and you had negative 200. Anyway, you had a graph like this. And if you make 50 hats, then you earn $100. And if you make 70 hats, then you earn $200. But if you make 30 hats, you break even. If you only make 20 hats, then you're negative this. And that number right there is 0, negative 200. Does that situation, or what does that mean in context of the story? If you make 0 hats, you're going to lose $200 because you had to buy the hat maker, right? Does that situation make sense in the context of the scenario? Yes, it does. And if you only make 1 hat and you sell it for 10 bucks, so 1, negative 190, 1 hat you'll recoup 10 of your investment dollars, and that totally makes sense. So sometimes the y-intercept fits the model in a relevant way, and sometimes it doesn't. And in the case of the foot and height, it simply doesn't. Okay. Any questions? All right, get to work.